easing. So, Mr. Ising was, in the spirit of statistical mechanics, was trying to find a model to describe microscopically magnetism. Okay? And in particular, what he wanted to describe is how a system gets magnetized. So how magnetic order comes out from microscopic interactions. So in order to do that, he cooked up a model which is the simplest possible ever model of a ferromagnet to paramagnet phase transition, in which the spins are described by what are known as Ising variables, sigma I equal to plus or minus 1. Now you could ask me, is there a physical system in which spins are behaving in this weird way and are not orienting themselves in 3 dimensions? I mean, you know that spins are quantum mechanical operators that can have different absolute value, depends on the nuclei, on the electrons, on all kinds of details. But there are materials who are known as uniaxial ferromagnets, in which the magnetic order is possible only in one direction. Okay? It's possible, for example, well, the system, depending on crystal structure and on crystal fields, essentially selects one direction in which magnetic order gets, orientation of spins or magnetism happens. And so you can have magnetization, for example, in that given direction, but the magnetization vector cannot deviate from that line. And in this case, the Ising approximation is quite reasonable. Now, the energy function of the Ising model is very, very simple. It is given by minus j sum over I and j, sigma I, sigma j. Now, what does this notation mean? In general, this notation means interaction between nearest neighbors. So if you have a lattice, depending on what your lattice is, for example, there is this lattice, let me see if I can reproduce it. Well, never mind, let's not do strange things. If you have a lattice like a square lattice in 2 dimensions, it is clear that nearest neighbor interaction is going to connect bonds like this one, okay? But you're not going to have an interaction along the diagonal, because this is not nearest neighbor. This length is larger than this one. This is 1, this is square root of 2. All right? Now, in addition to this, the physics of this model depends very much. Now, when you have nearest neighbor interaction is not that crucial, but the physics of this model depends very much on what is the sign of J. Why? Because if J is positive, then what happens is that what is the lowest energy configuration? If J is positive. What is the lowest energy configuration if J is positive? -1. Everybody pointing actually up, because otherwise it doesn't really matter, up or down, because you have sigma I, sigma j. So everybody pointing in the same direction, right? So you would have the lowest energy configuration is going to be something like this. And you will have in the lowest energy state what is known as a ferromagnet. If instead J is negative, what is the lowest energy configuration? Let's say for spins put on a line. Okay? Let's say that spins are on a line. What is the lowest energy configuration? If J is negative. 0? No. So, if J is negative, minus J is positive, right? So, therefore, if you want to go to lowest energy, you might want to have sigma I, sigma J equal to -1 whenever possible, right? So, how do you get sigma I times sigma J equal to -1? Always. On a line. Yeah, that's right. So if you have a spin up here, the next one you put it down. And then if this is up, you put it down. This is up, you put it down. So you have what is known as an anti-ferromagnet. Okay? But when J is negative, you have to be careful because sometimes it can lead to complicated situations. For example, let us consider this lattice. Okay, so it's a triangular lattice. So on this lattice with J smaller than 0, what is the minimum energy configuration? Have nearest neighbor interactions. What is the minimum energy configuration? What is it? It's tough life, right? Because you say, look, let me say this guy is pointing up. Now this is a nearest neighbor, so I make it point down, right? But then this guy here is the nearest neighbor of this and the nearest neighbor of that. And he doesn't know what to do. Right? So in physics, when you have something that doesn't know what to do, you say that it is frustrated, which is true also in life. Okay? So you have frustration. And frustration is something extremely complicated to deal with in statistical mechanics. Can lead, for example, to what is known as glassiness, the fact that you have systems with many minima, many local minima in the free energy, etc., is a whole subject by itself, which is very interesting, very exciting, but is beyond this course on basic statistical mechanics, as you can imagine. Okay, so let me just make. I don't know if you're, when I was a student like you, I was spending hours in the library reading all kinds of books about things that I was not supposed to know. Okay? So here I'll write down some names: spin glass, glasses, glassiness, etc. If you want to sit down, you have half an hour and you want to sit down and do nothing reading these books, then you go inside the library, you know where Ramanujan is, right? You go to the left, up to the door that goes to the bar, and you go to the right, the last corridor. At the end, there are books about this stuff. Okay? I know the library by heart. I know where stuff is. Alright, so anyway, this is advanced. So we are not going to deal with this. we are rather going to stick to ferromagnetic interactions, which are already quite interesting by themselves. Okay? And in particular, so we're going to stick to J positive. And in particular, we're going to start, for example, with by showing that in one dimension, it's not possible to have what is known as long-range order at finite temperature in this system. What is long-range order is all spins oriented in the same direction. Okay, this is a cool way to state. It's a fancy way to state that all spins, you have a ferromagnetic state in this case. And what I want to show you now is that if you are in one dimension, the ferromagnetic state is unstable at any finite temperature. This is something that is known as the Pyres argument. I'm sure that is also known as Landau-Pyres argument by the rule that everything that has, some name has to have also a Russian name. But anyway, I don't remember. So anyway, so let's take this state. Okay, everybody is oriented up, and let me ask you, what is the...
Sorry.
Yes?
Did you push again?
No, actually I pushed the wrong button. I pushed the record, so the story about the Russian was recorded. I'm sure that nobody is going to listen to this lecture. Nobody from Russia, at least. So anyway, and if he is, okay, well, there is such a theorem. Anyway, so given this, all these spins pointing up, what is the simplest possible excitation you can generate in this system? Simplest possible. And what is the energy of this excitation? Excitation means you have a ground state which has energy minus J times n minus 1, because n minus 1 is the number of bonds that you have. So the energy of the ground state is minus n minus 1, the number of bonds, times K. And now I want to know what is the simplest possible excitation that I can...
Minus C n minus 2.
Sorry?
Minus C n minus 2.
n minus 2? Well, you're absolutely right, but depends on the boundary conditions, right? So to get the n minus 2, you would need to flip a spin at the boundary, right? For example, if I take this spin here and I make it pointed down, I break one bond, this bond, that from minus J becomes plus J, right? And what I get is from minus J becomes plus J, and what I get is a change of energy delta E, which is 2J with respect to the ground state. Okay? But that depends on the boundary conditions. So let's say I take periodic boundary conditions to simplify my life. In this case, this kind of excitation at the boundary does not exist. And I have to necessarily, or let's say, no, actually, no, I'm wrong, sorry, I said something stupid. There is even if I take open boundary condition, okay? So let's take open boundary conditions. You're right, this excitation is the lowest energy excitation, the one in which I flip the spin of the boundary. How many such excitations I can generate?
Half of the number.
Sorry? So can I generate this excitation only by flipping this spin here and flipping the other spin at the other boundary?
Both at the same time?
No. One here and or one there. That's it? That's the only way to generate such excitation?
You could do it for the ones in the middle.
I can do it for the ones in the middle. How do I do it for the ones in the middle?
if you flip one in the middle, it means that you are changing the energy to this neighbor and this neighbor
If
too.
you flip only one spin in the middle, then you're breaking two bonds. And then the delta E is 4 times J, is not 2 times J. And therefore it seems that the only thing I can do is flip this guy at the end, flip the other guy at the end, and nothing else. But is this true? What else can I do? There is another excitation that I can generate in which the delta E is equal to 2J. Which one is it? So think for a second. The delta E to J, you obtain it when you break one bond. Which means when I break means that the two spins in the two bonds are antiparallel. In the bond are antiparallel. Okay? So let's start from the boundary. This guy is up, 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 and I decided that I want to break this bond. And therefore this guy is down. And I get a delta E to J. But then all the other bonds have to be satisfied. And therefore, what are the other spins?
Down.
All down. Down, 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 etc. You see, this is an excitation with respect to fully oriented system in which I flip a part of the chain down, but I break only one bond. And therefore, also in this case, I get a delta E equal to 2 times J. This excitation is known as a kink excitation. And again, if you go to the library in one of those sections, you will find a book called Kink and Solitons in nonlinear physics, which is very nice. Anyway, all right, so now we have these kink excitations. I mean, if you think about it, the excitation in which I flip one spin at the boundary is only a special case because it's the situation in which the kink moves all the way to the end, right? So now, how many ways I can generate a kink excitation? In how many ways I can generate an excitation with energy delta equal to 2J?
Just N maybe.
N minus 1. You were saying it correctly, but then you got, it was N minus 1. Why? Because a kink excitation is generated when I break one bond. How many bonds I have? N minus 1. And therefore I have N minus 1 ways to generate a kink excitation. Okay, so now, for the kink excitation, I know that delta E is equal to 2J. Sorry. I also know that the change of entropy that I get when I generate kink excitation, since I have N minus 1 ways to generate kinks, is going to be K Boltzmann log of N minus 1, right? Which for large N is roughly K Boltzmann log N. Okay? This means that with respect to the ground state, when I start generating this kink excitation, the change in the free energy is going to be delta E minus T delta S, which is equal to 2J minus KBT log of N. Right? And therefore you see that the log of N, when N is large, when T is finite, when you have a finite temperature, and N is large, this term is always going to win over this one. And therefore, by generating kink excitation, you lower the free energy. Which means that the state in which all spins are pointing up is not stable, because if you generate excitations and lower the free energy, that is not the equilibrium state that you're going to have at finite temperature. Okay? By definition of Helmholtz free energy. Clear? So this argument tells us no ferromagnetic order. In one dimension. Okay? This is a special case of all kinds of theorems that tell you when you can or when you cannot have phase transitions, which are known as Merlin-Wagner theorem, etc., etc. I'm sure that sooner or later you will see all this stuff in life unless you do ab initio calculations with a computer, in which case you will be expert of other stuff. Okay?
Sorry. If
Yes.
we fine-tune the temperature in the way that delta F is 0, what happens at that point? Is it something?
Well, that depends on n, right?
Yeah,
It's
we
going
have
to
fixed
depend on
number
n. Well, yeah, but it's a you can do that, but then you can have excitations in which you have 2 kink excitations, 3 kink excitations, etc., etc. I mean, and those are going to drive you towards disorder anyway, right? So because if you think about how many ways do I have to generate how many ways do I have to put 2 kinks, a kink and an anti-kink in my system, n times n minus 1 times n minus 2. So the entropy is going to be log of n minus 1 times n minus 2, which is log of n squared, getting factor of 2 in front, etc., etc., etc. So overall, at the end of the day, all this argument just tells you that the system is driven towards disorder. So the equilibrium state tends to be a disordered state. Okay? If you fine-tune, you would need to account also for higher order excitations, and then life is going to be more complicated. All right, and probably also sub-leading corrections will matter, because here, for example, we neglected corrections that go like 1 over n, because we neglected the factor of 1 here. But if you start fine-tuning, you have to account for this n, and then n minus 1 times n minus 2 becomes important, so life is complicated. Anyway, all right, so there is no long-range order. Now, in a sense, if you think for a second, the fact that you have all spins pointing up is a particular situation, peculiar situation, because if you look at this Hamiltonian, in general is invariant under the operation in which all sigma i's are set equal to minus sigma I, right? You flip the sign of all the spins. And this operation is called Z2 symmetry. Z2 is the modular space in which 1 plus 1 plus 1, well, everything is equal to, I mean, you always go back to 0, 1, 2 is equal to 0, etc., etc., etc. Everything is modulo 2. All right. So the fact that in the ground state we have all spins pointing up, or in any, if you are in higher dimensions, not only in the ground state, in 3 dimensions, for example, you can have long-range order at finite temperature, is an example of what is known as spontaneous symmetry breaking. Spontaneous symmetry breaking. Why spontaneous? Spontaneous because the Hamiltonian is invariant under a symmetry. The equations are going to be all invariant under the same symmetry, but the solution is not. And indeed, If you take all spins pointing up, you perform the symmetry and the spins will be pointing down. So you have two equal energy states, but the system is going to be in one of them, not in both of them. Now, spontaneous symmetry breaking is something that happens in systems only in the thermodynamic limit, okay? Which is also a situation where you do see phase transitions and so on and so forth. If you're not in the thermodynamic limit in the long run, you don't see spontaneous symmetry breaking and you blah, blah, blah. Now, all right. Now, this said, all of this was just a lot of blah, 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 blah. Now, fortunately, the easy model in one dimension and in two dimensions can be solved exactly. What does it mean can be solved exactly? It means that you can compute exactly the partition function. All right? Now, in two dimensions, the solution is rather complicated. It requires some advanced technology. I will perhaps tell you once we do the transfer matrix method, I will sketch for you how it is done in two dimensions, but it's rather complex. It's not easy. In one dimension, instead, is very easy. Okay, statistical models, like discrete models like this one in one dimension, can be easily solved in a variety of ways. So let's start with the simplest, and then we will go on with the more complicated ones. Okay? All right. So the simplest method to solve the easy model in one dimension is called the recursion method. All right, the recursion method works as follows. You have to compute the partition function of your model, which is the sum. Okay, so partition function, as we said last time, you have to decide what are the statistical configurations of your system, and the statistical variables are the spins that can be equal to plus and minus 1. Then you have to sum over all possible configurations, sigma, and then e to the minus beta times the energy function, which is our Ising Hamiltonian that I wrote down before. Now, if you spell what I just wrote here, this is equal to sum over sigma 1 equal to plus and minus 1, sum over sigma n equal to plus and minus 1 of e to the beta j sigma 1 sigma 2 e to the beta j sigma 2 sigma 3 e to the beta j sigma n minus 1 sigma n, where I took open boundary conditions, okay, not periodic boundary conditions. In principle, it should not matter in the thermodynamic limit, okay? The boundary conditions that I choose, I mean, the reason you can do calculations in solid state physics with periodic boundary conditions, even though you have never seen a table folded as a torus in 3 dimensions, is because the boundary conditions in the thermodynamic limit are completely irrelevant, and therefore we can, you know, cook up some mathematical instruments to simplify our life. In this case, it's more convenient to use open boundary conditions. All right, so now you notice with open boundary conditions, for example, that if you look at the last spin here, it appears only once in this set of products, okay? Only in the last term. And therefore, I can think of taking this sum, making it advance here, and sum explicitly over sigma n in this term. What I mean is, I can write this as sum over sigma 1 equal to plus and minus 1, sum over sigma n minus 1 equal to plus and minus 1 of e to the beta j sigma 1 sigma 2 blah 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 sum over sigma n equal to plus and minus 1 e to the beta sigma j sigma n minus 1 sigma n. Okay? Clear? Great. So now, what is this sum equal to? This is equal to up to a factor of 2, right? So is equal to 2 cosh of what? Beta j and sigma n minus 1. Okay? But now, does this depend on sigma n minus 1? Sigma n minus 1 can be equal to plus or minus 1. Does this depend on sigma n minus 1? No, because the cosine hyperbolic is an even function. And therefore, no matter what is sigma n minus 1, this is 2 cosine hyperbolic of beta j. You see? And therefore, what I just discovered is that this sum will produce for me 2 cosine hyperbolic of beta j. The sum that is left behind, this one, is what? This one, the sum that is left behind, is the partition function with n minus 1 spins. All of them but the last that I integrated out. And therefore I discovered that my partition function z is equal to z n minus 1, 2 cosine hyperbolic of beta j. Okay, so I discovered this is Zn. I discovered what is known as a recursion relation. That is why it's known as a recursive method. Great. So now, what is this recursion relation producing for us? Well, let's iterate it. So we'll get Zn minus 2, 2 cosine hyperbolic of beta j to the power to the power of 2 equal to blah 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 blah. I continue. I will get at the end of the day z1 times 2 cosine hyperbolic of beta j to the power n minus 1. What is z1? What is it equal to? z1. What is it equal to? This is the toughest question of the whole course, right? I mean, every year students start thinking about, what is Z1? It's the partition function of one spin. What is it? One. You're close to it. Let's do it like this. A, 1. B, pi. C, 2. What is it equal to? 2, of course, because 1, I said no, pi cannot be, and therefore it has to be equal to 2, right? It's certainly equal to 2. Why? Because, well, you have to think about what is Z1. This is the sum over sigma 1 equal to plus and minus 1 of what? Well, if I integrate out always the second spin, the first one remains without a partner, right? Is alone and therefore doesn't have a Gibbs weight, and therefore I just have this without the exponential, and this is equal to 2, right? That's it. So therefore I get that this is equal to 2 to the n cosine hyperbolic of beta j to the power n minus 1. And in particular, the free energy is equal to minus 1 over beta log of z, which is minus kBt log of whatever, 2 to the n cosine hyperbolic of beta j to the power n minus 1. Great. Now, if you're given this, then, okay, suppose that you have a crazy professor who doesn't know how to do calculations, and you don't know whether you can trust this result or not. How do you check it? Limits, exactly. So what do you compute, for example?
N equals 1.
Well, n equals 1, yeah. Great. N equals 1, you see that you get it. N equals 1, you will get k Boltzmann t log of 2. Great. Works. N equals 1 works. Fantastic. What else?
T equals 0 maybe?
Exactly. So we want to take the limits of t equals 0, t equal to infinity, but we want to take it for something we know how to calculate without doing calculations. So for example, we compute the internal energy, right? So the internal energy is minus d beta log of z. And if you do the calculation, you will get minus n minus 1 j tangent hyperbolic of beta j. Now, when temperature goes to 0, what should we get for internal energy? When temperature goes to 0, what should be the internal energy? 0? No. When temperature goes to 0, what should be the internal energy? Exactly 0. When the temperature is exactly equal to 0, what should be the internal energy? Should I do ABC or you come up with an answer?
Ground state of the system.
Ground state of the system, and therefore it is
J and minus n.
minus j times n minus 1. This is important. When I had a magnetic field on each spin, it was minus h times n, right? The ground state. All spins pointing opposite to the magnetic field. But in this case, what is important is not the site, is the bond. That is why you get n minus 1, because n minus 1 is the number of bonds in the chain. Okay? So in this case, we should get that our energy is equal to minus j times n minus 1. Does it come out?
Mm-hmm.
Yes, it does, right? When temperature goes to 0, beta goes to infinity, tangent hyperbolic goes to 1, j is positive, and therefore you get this. Now let's see when temperature goes to infinity. What should I get for the energy when temperature goes to infinity? 0. Why? That is exactly the right movement that you have to do. So, if you would have done this, I would say no. It's this. Okay? Because you have equal probability of each bond to be satisfied or not. Right? To have spins parallel or anti-parallel in this way. Doesn't really matter. You can do whatever you want. Okay? And therefore you should have an energy equal to 0. But when temperature goes to infinity, beta goes to 0. The tangent hyperbolic goes to 0, as beta goes to 0, and therefore you have 0 energy. So everything looks fine. Now, if you really want to check yourself to the extreme, what you could do is compute the entropy, which is minus df dt, And if you compute the entropy, what should you expect? I'll let you do it at home, but when temperature goes to 0, what should be the entropy?
It's -8.
Log of 2.
0.
Be careful.
Log of 2.
No, it's not 0. You have to be careful here, because you're breaking the symmetry, and therefore at 0 temperature you have two states, all spins pointing up and all spins pointing down, which are equivalent. Okay? And therefore the entropy will come out to be K Boltzmann log of 2. You see? It's important. So when temperature is equal to 0, you will have K Boltzmann log of 2. When temperature goes to infinity, what is going to be the entropy?
Diverging?
Well, it depends on what. I mean, with what?
I mean, it goes to infinity. It gets really large.
Yes. But how large?
Exponential.
2 to the power of n related.
Logarithm. Yeah, 2 to the n states.
Yeah.
Right? Because as usual, the same story. Infinite temperature is always the same infinite temperature. It's boring infinite temperature, as you can imagine, right? So when you take it to infinite temperature, each spin has equal probability to be up or down, and therefore you have 2 to the n states at infinite temperature that correspond to 0 energy, and therefore you will have an entropy which is K Boltzmann times n times log of 2. And if you do this calculation and take the limits, you will be able to check explicitly that it comes out. Alright? So now, one last thing that we can do with this exercise is compute the correlation function. So the correlation function, I already defined it. Let me redefine it. The correlation function at distance r is defined as sigma k plus r, or if you want is equal to 1 over zeta n sum over sigma e to the beta h sigma k plus r. That's the average of this stuff with respect to the Gibbs distribution. And now it turns out that typically a correlation function at finite temperature decays exponentially. So we'll go like e to the minus r divided by some length psi that depends on temperature. This psi of t is called correlation length. Okay? It's called the correlation length. And in particular, whenever you have, let's say, when you have long range order, right? So you know that if this guy is up and you look at there, close to the food, what is the other spin doing? Well, he's also up because you have long range order. You have an ordered state, a ferromagnet. If you have a disordered state, completely disordered state, if this guy is up, you look at his neighbor and you don't know whether it's up or down. It's completely uncorrelated because the state is disordered, is random. So psi of t essentially determines the range within which you have correlations in your system. If you have long range order, psi of t goes to infinity. The correlation length goes to infinity, right? Actually, this is true at the critical point. Well, we'll discuss this. But if you are in a state which is disordered, psi of t is finite. Perhaps this guy knows a bit of what this other guy is doing at finite temperature, not infinite. But if you go farther away, there is no correlation whatsoever. The guy there, close to the chokes, flips the way he wants. Okay? Clear. So what we should expect in our model is that psi of t should be finite at all temperatures, because we don't have long-range order at finite temperature. But if we take t going to 0 for this one-dimensional Ising model, then we should have psi of t going to infinity, right? Only at 0 temperature. Okay? Diverging only at 0 temperature. So let us now compute this and see what comes up. So the way to calculate this, so let's use the magics of... that's interesting. I want to see it. It doesn't appear. What is going on?
So you think the other thing.
Ah, interesting. Okay, and sorry, I was practicing with my toy. All right. So now, what did I want to say? There's one way. You see, in the Hamiltonian, you have only nearest neighbor interactions. While here, you have a product of two spins that are at a distance r. And now you can rewrite this as sigma k plus r. You can rewrite it as sigma k plus 1, sigma k plus 1, sigma k plus 2, sigma k plus 2, sigma k plus blah blah blah, all the way to sigma k plus r. Why? Because sigma k squared is equal to 1, because sigma is equal to plus or minus 1. And therefore here I'm writing sigma k times 1 times 1 times 1 times 1 times 1 times 1. And now I can rearrange this by splitting sigma k plus 1, sigma k plus 1, sigma k plus 2, sigma k plus 2, sigma k plus 3, etc., 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 all the way to sigma k plus r. All right. Now, suppose that now I had a partition function z, which was equal to sum over sigma e to the beta sum over I ji sigma I plus 1. So I get a different j for each bond. Okay? Well, if I get this partition function, it's very easy to redo the calculation we have done before. You would get 2 to the n product I from 1 to n minus 1 of cosine hyperbolic of beta ji. If you do the recursion method for this partition function. But most importantly, when you look at this, you see that if I now start taking derivatives with respect to beta ji, I'll pull down products of this type. Okay? And therefore I can pretend that my, in other words, dz d beta ji is equal to sum over sigma e to the beta sum over I ji sigma I plus 1 sigma I plus 1 when I take a derivative with respect to beta ji. Therefore, it's clear that sigma k plus r is nothing but the derivative with respect to beta jk, derivative with respect to beta jk plus 1, etc., derivative with respect to beta jk plus r minus 1, of z divided by z itself. Right? Because every time I take one of such derivatives, I'll pull down sigma k plus 1, sigma k plus 1, sigma k plus 2, etc., etc., etc. In other words, if you want, this is going to be equal to the average of sigma k plus 1, sigma k plus 1, sigma k plus 2, etc., 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 all the way to sigma k plus r. Every time I take a derivative, I'll pull down one of these products. Okay? But now I know what is z. When I take a derivative with respect to beta j, right? I go from cosine hyperbolic to sine hyperbolic. In the denominator, I remain always equal to sine hyperbolic, and therefore, if I do this calculation, fill up details at home. If I do this calculation, I will get at the end that this is equal to the product over I from 1 to n minus 1. Sorry, no, not to n minus 1. To k plus r minus 1, and this is k, of the tangent hyperbolic of beta ji. And now if I go back to the original problem I was interested in which all ji are equal, this is tangent hyperbolic of beta j to the power r. So this is my correlation function. Now it's evident that this correlation function decays exponentially because the tangent hyperbolic is a number smaller than 1, right? It's a positive number smaller than 1, therefore if r grows, this is going to go exponentially to 0. If you want, you can rewrite it as e to the minus r divided by xi, and xi will come out to be equal to minus 1 over the log of the tangent hyperbolic of beta j. And now you see that if the temperature goes to 0, beta goes to infinity, tangent hyperbolic goes to 1, but to 1 from below, and therefore this stuff will go to plus infinity. Okay? As expected. So everything is fitting with our expectations. Alright, so now that we know everything about the easy model, it's time to do a little exercise.
Can I ask a question?
Sure.
Can we prove that this sigma k plus r is the multiplication of all the connections?
Can I prove it? Yeah, sure I can. Look. So, let's take sigma k plus 2 for simplicity. Okay? So this is equal to sigma k times sigma k plus 1 squared. Why? Because sigma k plus 1 is equal to plus or minus 1. And therefore sigma k plus 1 squared is always equal to 1. Right? So this is sigma k times 1 times sigma k plus 2. We agree on this? Now 1, I can write it as sigma k plus 1 squared.
Okay.
And now this is equal to sigma k plus 1, sigma k plus 1, sigma k plus 2, by the associative property of the multiplication. because multiplication makes a field, an algebraic field, whatever. QED, quantum electrodynamics. Great. Okay, exercise. The exercise is about a model that is known as the Potts model. Not the Potter model, Potts model, the Harry Potter model. So what is the Potts model? The Potts model is a model in which our spins, instead of being up or down, point in some directions, more than two directions. For example, you have a spin that can point, let's say, 1, 2, 3, 4, 5, 6, 7, 8 dimensions. So you would say that here you have a Potts variable Q that has 8 possible configurations, and sigma I can be equal to 1 all the way to Q. In general, we would say that the Potts model is a model in which sigma, which is our statistical variable, can take Q values, Q possible values. And these Q possible values represent, for example, Q possible orientations of a spin in space. Okay? So for example, if I have 3, so sigma, if I have a 3-state Potts model, sigma can be equal to 1 or to 2 or to 3, and that could represent, for example, something like this, the 3-direction on a triangular lattice in 2 dimensions of a spin, and so on and so forth. So what is important to know is that for the Potts model, the statistical variable can have Q values and vary, for example, from 1 all the way to Q. Okay? That's the Potts model. So the spin thing is just to represent visually what it can physically correspond to.
But for each of the Q states, the sigma 1 squared is still 1? I mean, the length of that state is still 1, or?
As you will see, it doesn't really matter. So let me write it down, because your question is important depending on how you define the energy. So the energy of the Potts model is defined as follows: is equal to minus J sum over I and J delta sigma I sigma J. What does this mean? If sigma I, and delta is a Kronecker delta, right? So if sigma I is equal to sigma J, then this is equal to 1. If sigma I is not equal to sigma J, then this is equal to 0. So you see that the length, the question of the length is not important. I can make sigma vary from 1 to Q, and when, for example, 2 neighboring spins are equal to 6, then I have 1. When 1 is 6 and 1 is 5, I have 0. So what is important here is to be equal or to be different. Okay? When you're equal, you get a reward, minus J. When you're different, you don't get it. Okay? You can, of course, make an antiferromagnetic case in which you take a J negative, in which case you, well, life is complicated, you will turn off by being equal. All right, so now, what is the symmetry of this anomaly? This is a tough question, guys. What is the symmetry? What is the symmetry of this energy function?
In the ground state?
No, in general. In general. What is the symmetry of this guy?
Permutation.
Absolutely, permutation. Why? because it doesn't really matter. So since what matters is to be equal or to be different, right, for the energy, it doesn't really matter whether I call my configurations 1, 2, 3, 4, 5, 6, 7, 8, or A, B, C, D, E, F, G, blah, 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 or I swap the order of the indices, or I do whatever. Whenever I take my Q equal to from 1 all the way to 8, and I perform a permutation transformation on these indices, in which, for example, 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3, etc., 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 then it's clear that the energy is invariant. Why? Because if before two guys were giving me a minus j because they were both equal to minus 1 to 1, now they will be both equal to 2. I don't care. If before they were giving me the same energy because they were both equal to 3, now they will be equal to 4 after I perform the permutation symmetry. And I don't care, because what is important is just to be equal or to be different. Okay? So therefore I have any permutation, any permutation of Q states, permutations of Q elements. Any permutation of Q elements leaves the energy invariant. So this is the symmetry group of my model. Alright, so now let's compute the partition function Zn. So this is going to be equal to sum over sigma 1 equal to from 1 to Q, sum over sigma n from 1 to Q, and then you're going to have e to the beta j delta sigma 1 sigma 2, and then e to the beta j delta sigma n minus 1 sigma n. Okay? Here? Okay, so now I use my recursion method. This is going to be equal to sum over sigma 1 equal from 1 to Q, e to the blah blah blah, e to the beta j delta sigma 1 sigma 2, and blah blah blah, and then I will have sum over sigma n equal to 1 to Q, e to the beta j delta sigma n minus 1 sigma n. So this is equal to what? This sum is equal to what?
Q times
So is equal to what? Sorry? Okay, so that's one part of the answer.
and then how many
Plus
numbers when they are not equal?
And how many? How many ways you have not to be equal? Q minus 1. So it's going to be Q minus 1 plus e to the beta j, right? So it's going to be e to the beta j plus Q minus 1. Okay? So that's the answer. And you see that it does not depend on sigma n minus 1. Because sigma n minus 1 has some value. I don't care what it is. It's some fixed value. And there is only one way to be equal to sigma n minus 1, and there are 2 minus 1 ways not to be equal.
No coefficient in front of exponential?
No coefficient. Why should there be a coefficient? There is only one way to be equal. And there are 2 minus 1 ways not to be equal. Right?
Ah, yeah.
Okay, so therefore this is equal to z to the power n minus 1 times q minus 1 plus e to the beta j, and therefore if I iterate this recursion I will get z1 times q minus 1 plus e beta j to the power n minus 1. What is z1?
1.
What?
Q.
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 Q, right? Because before it was 2. It was the sum over all possible configurations of nothing, of 1, and therefore was equal to 2. Now it's the sum over all possible configurations of one variable, which are q, of 1, which is q. Okay, so it's q times q minus 1 plus e to the beta j n minus 1. All right? Great. So now, are you convinced?
Kind of.
Perhaps. Sometimes. Let's say it's sometimes equal to q, depending on the mood. Okay, so now, compute the free energy. Free energy, well, you can compute is minus 1 over beta log of z. And now you can compute from the free energy the internal energy. Play the same game as before, so minus dt beta log of z. So here, do it. Let's just do it. Just do it. And what we will get at the end is that this is equal to minus n minus 1 times j times e to the beta j divided by q minus 1, just a second, plus e to the beta j plus q minus 1. Okay? Now, I wrote this answer on purpose wrong. I have the correct answer here. But here I made a mistake on purpose. Because I want you to get it, to check it. To see that there is a mistake in this answer. How do you get it? Take the limits, right? So what should be the energy at 0 temperature? What should be the energy at 0 temperature? For this system. Minus n minus 1 times j, right? Because it's the same story. All spins are going to be pointing in one direction, it doesn't matter which one. There are q equivalent directions, but they will be pointing in the same direction and minimize the energy by satisfying each single bond. And therefore I will have an energy minus n minus 1 times j. So t goes to 0, the energy should go to minus n minus 1 times j. Does it work? temperature goes to 0? No, it's okay.
Temperature goes to 0, beta
Temperature,
goes to infinity.
beta goes to infinity,
Yeah, it goes against
beta goes to infinity.
It's 1 over 1. What's with
It's 1 over what? If beta goes to infinity,
No,
this
the
dominates.
expression that's written, it's like equal to 1 at any beta.
This is. Ah, yeah, that's right. Yeah. Let's put a q minus 2. You're right. Q minus 2. Okay, let's not do stupid things. This is the correct answer. You're absolutely right. So does it work? It works,
Yes.
right? When beta goes to infinity,
Q
this
minus one.
divided by this goes to 1, etc., etc. Now, when temperature goes to plus infinity, what is the energy? What is going to be the energy?
Exponential is
When temperature goes to plus infinity, what is going to be the internal energy?
Multiply 1 by q minus
No, don't check this. Let me first guess what should be the internal energy, otherwise we reverse the problem.
0.
Wrong!
Ah, yes, because
It
this-
doesn't have to be 0. It's
Yeah.
not equal to 0.
Yeah.
That's exactly
Yeah,
where you
yeah.
get it wrong,
Yeah.
right? And everybody every year gets it wrong here, right? There's always the first answer is always wrong. I was looking forward. Why it's not equal to 0? You have to think. You have to think before giving it. You say disordered 0, absolutely 0. No, disordered. Is disordered equal to 0 in this case? Let's think about it. Disordered means that I have one configuration in which I will get an energy minus J, and all the other configurations in which I will get an energy 0.
Yeah.
Right? And therefore, the average energy, right, because all these configurations are equally probable, the average energy is going to be minus J per bond, is going to be minus J divided by Q. Right? Because in one configuration I have an energy minus J, so in other words, sorry, what is going on? Teaching. So, in one configuration I will have an energy minus G. In all the other configuration I will have plus 0, plus 0, plus 0. And I will have Q minus 1 configurations that give me 0. Right? And then I have to divide by the total number of configurations because I want the average energy. The total number of configurations is Q. In the previous case, I was getting 0 because for one I had two configurations. One was giving me minus J and the other one was giving me plus J. That's why I was getting 0. But now I'm not getting 0. I'm getting, for each bond, minus J divided by Q, and then I have to multiply by the number of bonds, times n minus 1. And now you see that if I take temperature goes to infinity here, you see that here goes to 0. I get Q minus 1 plus 1. This is 1 over Q. And this goes to 1. So I get minus n minus 1 times J divided by Q, which is exactly what I should get. Okay? So be careful. This teaches you something. Never take for granted the result. Okay? You have to think all the time in physics and in life in general. I mean, in particular when you're buying something or selling. Anyway, I think we are essentially done. Well, no, let's do the entropy. Come on, I don't want to do the entropy next time. So the entropy, if you do the calculation of the entropy, which you do it, just do it, you will get some complicated answer log of q plus n minus 1 log of q minus 1 plus e to the beta j minus n minus 1 beta j e to the beta j divided by q minus 1 plus e to the beta j. Alright, so this is the entropy. I did a calculation, it's just a derivative, you can do it at home. I mean, it's not difficult, but please do it. By the way, from next week you will get Silvia doing the exercises. But already doing these little calculations will help you out. Now, let us guess what should be the entropy at zero temperature and at infinite temperature. Zero temperature, what should be the entropy? Kb log of? Absolutely. Zero temperature. K Boltzmann log of Q. Because I have all spins pointing in the same direction, but I have Q the same directions. So I should have K Boltzmann log of Q. Infinite temperature. What should be the entropy? What should be the entropy? Infinite temperature. Pi. Should be beautiful. The entropy at the infinite temperature should be beautiful. So what should be the entropy?
Q to the power of n. I mean n log of q.
N log of q. So it should be K Boltzmann log of q to the n. Why? Because for each spin I have q equally probable states, and therefore for the whole set I have q to the n possibilities. That is the number of states that correspond to an energy minus j over q times n minus 1, not 0 in this case, and therefore I will get this entropy. Okay? So this is the entropy at infinite temperature. If you look at this and take the limits, you should get what we just wrote. That is important. Look, I will never say it enough. In physics, calculations get really nasty. Sometimes, not always. But if you want to know whether a nasty calculation is correct or not, sometimes you're not even able to simplify too much things. It's important to have some intuition and know what is the result that you should get in some limited cases. Okay? Also, when you will do the final exam, it's crucially important when you get to, well, I will ask you explicitly, but it's important when you get to the end of a calculation to check yourself in the limits. Otherwise, you never know whether what you wrote is correct or not. You cannot know, particularly when you do research, right? I'm preparing researchers. I'm not preparing, football players. Okay? Good. Excellent. So, see you on Friday.